While some people are busy flying around the world, here I am, just being Canadian. Hello boys and 5% grills. This video is about bytes and bits because I'm tired of explaining stuff in the comments section. And also because I'm tired of seeing this kind of code. So today, we're gonna go low level and we're gonna be talking about byte and bits. Mainly how I store multiple booleans inside of a byte, short, int, you name it, we just store booleans everywhere, and this is to minimize the memory consumption, which is quite useful. So I remember we've used this for the mobile game tutorial. This is how we save which item we bought instead of the shop, just storing multiple booleans instead of an int. But we're moving towards more multiplayer stuff, especially with the new network transport, which I am looking at right now, by the way. It's quite tasty. But yeah, since we want to pass less data through the bandwidth, if we manage to store multiple information instead of a single int, single byte, it's always better. We reduce the size of the bandwidth. Okay, so as I mentioned, we've used this concept a long time ago on the channel. I get a lot of comments that are like, hey, this is wonderful, it works, but what the hell is it, right? So here it is. Today, we're going to be speaking about byte and bit and how to store multiple booleans inside of a single int. Cheers. Alright, let's get started. We are currently in Sublime, so I can explain some stuff through text, very big text. And we are going to get started with some high or low level things, yeah. Let's start with a bit. What is a bit? A bit is a simple character representation of on or off. You see that in binary code. So it's a value, actually, it's a field that can hold two values, either 0 or 1. Nothing else. You can't go to 2, you can't go to 3, 4, 5, 6. You can't do any of that. So it's 0 or 1. Now, next one is the byte. A byte is basically 8 bits next to each other. In decimal representation, what is this exactly? It's a number in between 0 to 256, 255, because we include 0 in this case, but that's like 256 values. You see that everywhere. So to give you an example of what a byte is, couple of examples we could take. I'm going to take the RGB format. So when you define a color in some of the software, in a lot of software actually, you can tell that every single one of these colors, so red, green, and blue, they all hold their data in a byte. So you end up having 3 bytes to represent red, green, and blue, and sometimes a fourth one for alpha. You'll see this in Photoshop, you'll see this in a bunch of different places. So assuming we want to have like a nice little cyan color, if we want to have this color presented as byte, here they are. So red 0, green 252, and blue 255. So blue is at the maximum values. Now if I try to manually edit the blue and like go beyond that, so 256, you're gonna see that you need they call it an int here, so you need something in between 0 and 255. Obviously, because that doesn't fit. Like if it's not in between that, it doesn't fit inside of a single byte. Right. Even though they call it int in their tooltip, which is kind of weird. Okay, moving on to the next data type, we have the U short for unsigned short, and this one goes up to, what's the number? 65535. Yeah. If you don't know the difference in between the unsigned short and a normal short, then I will be explaining that in a moment. So don't worry about that. But before that, we'll move on to the next thing, which is a uint. Similar as a normal int, but this one is unsigned. And the value you can hold in between a hint is the values are in between 0 and 2 billion something. Okay, so we know that much about these fields. But why exactly is a bit able to hold more information than a uint? Like what's the base reason? What's the physics that allow that to happen? It's not really physics, whatever. What's the reason, right? Here is the reason. A bit, as I said, it's just represented as a 0 or 1. So you only have this little space in memory, and this one can be a 0 or 1. This is how machine code is being represented. It's always 0 or 1. You guys know about it. It's binary code. It is basically only 0 or 1. It can't do it's on or off. Right. Don't need to go any further than that. The difference in between a bit and, say, a byte is the amount of those you have. For a byte, you have a total of 8 of those. And with those 8 bits, because now every single one of these, they're called bit. For every single one of these bit, you can have the value 1 or 0. Just like you had at the top there. They can't do 2, they can't do 3, 4, 5, you can't have any of that. It's either on or off. With a total of 8-bit, you can represent a number that goes as high as 255. How does this work? Well, here is how we represent these numbers using bits. So from now on, we'll be referring as every single of those 0 or 1, we'll be referring it as bit, because that's what they are. Right. This is how we represent 0. This is how we represent 1. So 0 is equal to 0, I'll write it down here. 1 is equal to 1, and then you get to this point. This is equal to 2. Might be confusing, but what really happens here is that we add a new bit on the left, and this number becomes now 2-bit long. And with a 2-bit, you can represent a number like 2. If we want to represent 3, this is the logical way to go about it. The logic here is that as soon as you can't represent any more number with the amount of bit you have, you increment it. Now if we can't represent any new number with this, then we're going to go ahead and add a new byte on the left. And we end up with this. 100 is equal to 4. Technically it's not 100, it's the third byte being lit, or being active, and that's equal to 4. If we want to represent 5, we have to say, okay, the third bit, the second one we don't need, and the first one is equal to 5. So this is how it goes. You always go from that one side to the other. Then we have this, which is equal to 6, and then this, which is equal to 7, and finally you end up on 8. And this is how you represent binary code. Right. Usually binary code is never represented the same way as I have here. It's always in chunk of 8-bit. Just like the way I wrote it down here. Why is it like that? Because we like to represent bytes in computer and not so much bits. So bit, we're kind of done with it. We know what a bit is. We know that a byte is made out of 8-bit. But we're not going to go beyond that. Now moving on to U-short, it's the exact same thing. So you just add more bit. In this case, you go up to this amount. So you go up to have a total of 4, 8, 16 bit. So this is what we call a 16-bit number. And a 16-bit number can go up to 65,000. Now, so we understand what is a unsigned short and a normal short, I will do the following. So this is a short right here, and the maximum value I believe is 32, wait, what is it? 65535 divided by 2. 3267, okay. Like this. So this is a short, and this is a unsigned short. It's going to be the same layout in memory. However, I got that wrong here. With a short, normal short, you can go negative value, but in the unsigned, you can't. Now, the only difference in between these two numbers is that one can go negative and one can go much further. So, you know, these two numbers, if you sum them up together, will go up to 65,000. So how do we do this representation? What goes on here? Well, if it's a short, you're going to have one of the bit, usually the first one at the beginning, that is reserved to know whether or not it is a positive value or negative value. For example, I will actually take somebody else's example because I have a nice little graph. This is the number 53 being represented up here as a 8-bit number. Now, this is a signed on-bit number, so as you can see at the beginning, they use the first byte. This one's 0, which means it's going to be positive. Down here is the same number, but they only flip the first bit. Now it becomes negative, and it becomes negative 53. This is also why we cannot go as up as, or we can't go as high as 65,000, because we have one less bit to work with. So your number is only composed of that, and then if you want to know whether or not it's positive or negative, you know, you just flip the first one. The first one is only reserved to know if it's positive or negative, basically. So that's a U-short and a short value. Now the concept of unsigned will be applied to int as well. It will be applied to long as well. It will be applied over there. Quit. And finally, what is an int? Well, it actually depends. In Unity, by default, an int is 32-bit. So it looks something like this. Sometime an int is 16-bit. Sometime an int is even 8-bit. It depends which engine you're using. It depends which definition of int they're using. Everybody kind of declared their own int, but in Unity, a int is 32-bit, and it can go as high as this number that I can't pronounce. Okay, so why did I go through the trouble of telling you all of that? Because we are going to be leveraging this in a couple of cases. I know I've been doing that in a lot of videos, and it's something you guys come back to me and you're like, hey, that works, it's cool, but what the hell have I done, right? And we're going to be explaining it today. So, I'm going to be taking a single byte. This over here, the byte, is one of the smallest thing you can declare in memory. Why is that useful? Well, we know that a byte is in between 0 and 255, so that's a value in between 255, and we know that it has 8 bits inside of it. We can leverage that to store as much information as we can in this without declaring too much memory. And this is why, like, back in the days, memory really mattered. I'm feeling like memory will matter again one day because we're going towards network code, especially on our channel. So making smaller memory, smaller packed things will benefit us greatly. If you want to have some good networking code, if you want to send some code through the bandwidth, the smaller it is, the better. And the more data we fit inside of it, the better our game can be as well. So I'm using the byte at quite a lot of places. In the last tutorial, the LLAPI tutorial, you guys have seen me talk about, you didn't see me talk, but I talk about getting an error message back as a byte, and saying that we could parse this byte to have a different amount of information. So the player was not able to log in because he doesn't have the right email, the email doesn't exist, that was not the right password. You could fit in a lot of information, in fact, 8 different information in that through a byte. And it's a good practice. In fact, Unity themselves, when they give you an error code, they give you an error code, right? They don't give you a error int, they don't give you a error text message, it's not a string, it's a code, and they can declare a big enum somewhere to know what the error is based on that error code. So, I've just quickly mentioned, this is a byte, and it can hold up to 8 different values. Why? Because we have 8 bit inside of it. Imagine those are all booleans. So, we have our bit over here, we'd like to say, assuming this is our inputs, we'll do inputs in a moment. This would be WASD instead of 000. Well, to know whether or not we're pressing on WASD, we could be simply playing down here with bit. So just like this, we're able to know with a single bit what the player is pressing on, for say. Like we could do something like that. Plus we have 4 additional. So assuming we want to do a little bit, want to go beyond that and do some inputs, say from League of Legends, so QERF, something like that, just keys around WASD. We could also know if the player is pressing it on this frame by toggling on some bit. So assuming our player is pressing on all the buttons, it would look something like this. If he's only pressing on WASD, then it would look something like that. We can leverage that and put it in a very, very small amount of memory. Let's try it out. So I'm currently in Unity right now. We'll be using modal behavior to create a simple script, have a look at our byte, how we interact with bytes inside of C# code, and then we're just going to run it. So, we're not bootstrapping anything, we're not using ECS, just classic stuff, super fast. I have a new script called byte tuto, for tutorial, I guess. And I'm just going to drag and drop here on the camera. It won't work because I don't have a modal behavior. Okay, let's do public class byte tuto, blah, blah, blah. Alright, that's better. I got my script over here, I got my byte tuto on top of an object so I can leverage update. Yeah, I don't need start, I'll just leverage update. Okay, so here how it is. We're going to be declaring a byte. We're going to do a private byte, call it input flag. You'll see why we call it flag in a moment, but now just imagine that this is our byte. This is what we said, right? This is our byte. It looks something like this in memory. Now, I'll quickly write down some input code and speed up the video because I know my microphone must be really annoying when I type. And here I have it running. Quite simple stuff. Every frame I reset my input flag to 0. So every frame I wipe everything we know about the keyboard. We're going to start over again, right? So clean slate. Now if I hold W, this is not a get key down, this is not a get key up, it's a get key. So if I'm holding W, we do a plus equal 1. What does it give? Of course, every frame you're gonna have 0 until I press on W, and then it's gonna be 1. Very, very easy, very, very clear. Now, let's go to the second one. So we said W. What if we do A? Well, we'll want to increment that by 2. Sounds fair enough. Okay, so we're gonna have number 1 if it's W, we're gonna have number 2 if it's A, and if it's both at the same time, we're gonna have 3. So we have a way of knowing whether we're pressing only on 1 or 2. What is that way? Well, I just said it basically. If we get 3, so if input flag is equal to 3, that means we're pressing both. I don't know why I was writing it. Yeah, so if it's 3, we're pressing both. If it's just 1, we're only pressing A. If it's 0, we're not pressing anything. So that's really cool because we get to know 3 different settings. Like there's 3 possibilities out there. I'm not going to test this out. You guys know this work. Okay, now if we come down here and we say the next one, S plus equal 3. Well, we have a problem here. What is that problem? We just said that assuming I want to know if I'm pressing on W and A at the same time, so I can do, say, a up, left, a diagonal move towards left and up at the same time. Again, screw English. I know that I'll have 3. But with this new code, if I don't press anything but S, I also get 3. So now what does 3 mean? Does it mean I need to go up and left, or does it mean I go down? This is where you need to remember this little layout of bytes. What do I mean by this? Well, what is 1? This is 1. What is 2? This is 2. What is 3? This is 3. Kinda doesn't work, right? Because this happens if I toggle these at the same time. What I need to do is toggle the 3rd bit. So 1, 2, 3 in this case. And if I turn this one on, I won't disrupt the 2 others. So I'm not playing around with this one byte. I'm not playing around with this one byte. I'm on my own at the moment. What is that number exactly? Well, that is 4. So here we go. This becomes 4. And finally, same thing applies for D. So WASD in this case. We need to actually shut down this one. We're not playing with the 3rd bit anymore. We're playing with the 4th bit. What is the 4th bit? 8. How do I know that? I just need to do ×2 every time. Making sure everything works, right? Making sure. Let's just conceptualize if everything still makes sense. Assuming I press on WAS at the same time, I'm going to get 1 plus 2, that's 3, plus 4, that's 7. That's right before the new number. It's like it's super convenient. Everything works. Everything is just amazing. Assuming I'm pressing on W and D at the same time, I get the number 9. So W is 1, D is 9, and there ain't no combination of anything else that's going to give you 9. Only W and D will give you 9. Why? Well, just look at the bit. That's what we do. We toggle on this bit, and we toggle on this bit. Nobody else plays with the 1st and the 4th bit. And that's how we do it. So if we want to keep on going, we know that a byte is 8 different bits, so we can add 8 different values in here. You know, well, you can do it here, so you can say, this is going to be my Q, my E, my R, and my F. Why am I using these values? I'm not sure, I just like binding those keys if I play a game that requires a couple of movement. Let me go fix that, I'll be back. So I've changed the comments, the green comments, so it reflects the right bit. Now, it's time for me to change the actual value incremented by. Without even having to check binary code, I know that the value is always ×2 of the last. So 16 in this case, then we end up at 32, 64, and 128. We said earlier that a bit only fits 255 values. So what if we take all of those and actually, try to add them up together, assuming we're pressing on all of them at the same time. 128, 64, 32, 16, 8, 4, 2, and 1. Amazing. Amazing. Are you starting to get it? Are you starting to know how we can fit all that information into a single bit? And that's a bit. That's not an int. If it was an int, we could go beyond. Like if it's an int, remember, that's all of this. We can add a couple of different values. You could lay out your whole keyboard on the hint if you want to. Well, no, there's more letters than that. Well, you can at least lay down the whole alphabet. Maybe not the whole keyboard. Well, definitely not the whole keyboard, but you can lay down the whole alphabet on the keyboard. So that's in a simple int. You use the same int to have like a score value or a health value in your game. well, it can fit all of this information, so this is great. Okay, moving on. We have this value. We have unique value for every different kind of combination of key you can click or touch. How do we actually check if one of them was clicked? Assuming that we have Q, we're pressing on Q, right? But we're also pressing on E at the same time. What if I only want to check if Q was pressed? Well, my number at that time isn't 16, so I can't do a condition that checks if input flag is 16, then do something, because it's not going to be 16 in this case. It's going to be 16 plus 32, because that's the number, that's the combination we're going to have. So 16 plus 32 is 48. If only Q is pressed, you only check for 16. But if Q is, you just want to know if Q was pressed in general, then you have 8 different conditions. You have 16, you have 17, you have 18 if you do Q and A, you have 19 if you do Q. Actually, you have way more than 8. You have a lot of conditions to check. Basically, that's unreliable, right? So what you're going to do instead is use bit operation. Now, if you're using .NET 4.0, which we all will eventually, if we're using Unity, we're moving towards ECS. I currently am on .NET 4.0, but if you're not, that's totally fine. Why am I saying this? Because in .NET 4.0, you have a extension of enumeration that has a function called hasFlag, and this will allow you to do what I'm about to do. Right. Right here is the piece of code you need to have if you want to test a single condition. So if, then you take your flag number, your byte in this case, the one you've been filling in, and you test against the number you want to test, the bit you want to test. Now this is 16 in this case because we know that 16 is the 5th bit. It's not really clear right now. We're going to make this better in a moment because right now it's really not clear, but this is the if statement you want to have if you want to check for a very specific bit. Here on the left, your value, the one, your whole number, the one that you've set at the top here, and then after that, the bit you want to check. In this case, 16, we know it's the 5th bit. It's not going to remain like that. It's going to be much clearer quite soon. Right now, it's kind of hard to tell. But yeah, we are basically isolating that bit and we're checking is it on or off. We're not looking at the rest of the number. And if it is on, well, we're going to do a small debug.log, just like this. Let's test this out real quick, just to know if it works. So I'll be playing the game. The console is running. I'm going to press E. If we press on E, we get 32. I'm going to press on R and E at the same time, 96. So that's those two numbers together. Actually, let's go easier. Let's do 1. So W, and then I'll press on Q, which will give us 17. 17 is W, so it's 1, plus Q, 16, and we know that Q is pressed. If we release W, we end up with 16, which is of course a number that tells you Q is pressed as well. And I'm going to go through all of them, so that's with A, S, D, E, R, F. Yeah, that's it. So the whole time over there, Q was pressed, and if I press on other key right now, you can see it doesn't do anything if I don't press on Q, so I don't get the debug.log. Good, so we just checked for this one. Now, it's all fine, it works, you can go and like start coding with this, create your movement state machine with that, whatever. But it's not really readable, right? It's not really fun to read. We don't really know what 16 is outside of that. If we change one thing, we have to change it everywhere. Which is obviously not a good way to go around in code. So we are going to be introducing enums. Yay! Input flag enum. Why not? What you like to do when you're creating this, when you're creating an enum for this kind of purpose, you just mark it as flags, which is under systems, I believe. Yep. And we're gonna do the exact same thing as we've done, but we'll put our numbers, so our hard-coded number, we'll put them up here in an enum. Let's start with none. None is 0. We know that if we don't press on anything, we'll get 0. Then W is equal to 1, A2, S4, D is 8, and we just move on to all the other ones. So what do I have? Q, E, R, F. So Q, E, R, then finally F. And this is what we get. Here you can see if I remove none, those are all the possible byte. Now, you can leave none. That's the cool thing. You can leave none. You can even declare more than that. If you want to have like some specific combinaison, if you want to have some specific blend in between keys, you can also declare more here. You can declare as much as you want. So assuming, well, as long as you're not going beyond 128, which is going to be the last bit. That's the last value you're going to have in your bit. But you can go here and say, assuming that I want to check if my movement keys are all pressed at once. So all movement key. You can do that by saying 1 plus 2 plus 4 plus 8. Is that that's actually possible? I didn't know it was. But you can calculate that this way. Or the proper way to do it is to reuse these and put pipes in between. Those are for bit operations. So W, A, S, and then D. And all movement key will now be equal to 15. We could say all movement keys like that, or we can say all movement keys also equal to 15. That will work because that's the combination of all the movement key together. Okay, let's actually be a little bit more fancy. Let's do vertical only. Vertical only would be W and then S. Horizontal is A and D. Cool. So this is fine. Now, how do we go and use it in our code? Well, what I like to do is we like to replace the byte by our enum. We'd like to have our enum now. Now let's go down here in our code. We're going to see that input flag and then the ampersand and 16 isn't going to work anymore. We can't test that against the int anymore. The only reason is that this is an input flag. It's no longer int. They don't have any overload with that. So instead, we're going to mix it with input flag dot q, because that's what we're checking, right? And it's going to make the code so much easier to read. As you can see over here, we can just check with the literal thing. We know now. If we read this code, we know what it does. Is what I'm trying to say. And something even better than that is let's have a look in here in the console down here. If I press on Q, you're gonna see that first Q is pressed. Okay, let's press on W instead. W is being spammed in my console. Now, if I do E, you'll have both of them at the same time. And even better than that, if we do W, A, you'll see W and A. But if we do W and S, you'll see vertical. Why? Because we get this number instead. We get horizontal as well. It's a little bit clearer. Good. Now we can also go in here and change our the code we had, because this is our hard-coded value we want to get rid of. We can do input flag .w in this case. Is this going to work? No, because what they're expecting is a flag value. So if you do a plus equal here, they're not necessarily fetching the value of w here. They don't really know what it is, right? They don't really, there's no overload for this. So instead you do a pipe sign, and this will lit up the bit. So assuming that you're on 0, then it's going to be 1 if you're using the pipe sign equal. So I'm going to go down here and start changing them all to pipe sign equal and then the proper input flag. And here they are. Everything is changed. We're going to do one more test, see if everything is good. And then you'll see that it's the same thing as before, pressing on different keys, and it works exactly the same way. Now quickly, you're going to realize that we kind of lost the definition of a byte here. A byte is 8 values. You are going to realize you can go much beyond 8 values over here, and that's because input flag, well, enum at the base, doesn't really inherit from a byte. I think it's an int 32, I'm not sure, don't quote me on that. So if you want to keep the same benefit as we had with the byte of just being really, really small in memory, you can go up here and actually inherit from byte. So instead of actually taking 32 bits, if it's an int, like I said, don't quote me on that basically, but the default value I think is an int, it's taking 32 slots, and you could go much further than that, and of course that's okay if you need that. But if you only need 8 values and less, make sure you inherit from bit. Now this input flag is going to be much smaller, and this field over here is going to be much smaller as well. I was going to end the episode right here, but I just realized that it might be good to tell you how to actually turn them off. We turn them on right here with the pipe sign, but it might be a good thing if I actually showed you something. So let me get rid of everything but W in this case, and also get rid of the reset every frame. What I'm going to be doing here is get key down and also get key Oh, if I press on W, I want to turn on the first bit. So I want to turn on this bit. If I release W, so that's on my on key release, I want to remove it. Now, to remove it, you gotta do the character I don't have on my keyboard. It's the hat sign. How do I do the hat sign on this? So we've got 94 over here, so 94. By the way, if you want to do the pipe sign, that's 124. So the hat sign that you probably have on your keyboard, but I don't, for some weird reason, will remove the byte. This is going to put that on 1, this is going to put it back on 0. We'll test this out right here. So not pressing anything, should have 0 being spam or none in this case. I hold W, and I release it, none. Assuming that I don't have this piece of code, we're going to be stuck on W forever, even when I release it, because we're not turning it off. So W, then my hands are up here. W is stuck. If I want to remove it, I gotta do the same operation, but with the hat sign instead of the pipe sign. Quality. Okay. This is actually where we're gonna be ending this episode, guys. I hope this was a little bit clearer, and if you end up running into this, because I'm gonna be using it at a couple of different places, especially the network, I'm using it in the movement system I'm making for the ECS. It's gonna be a short video about how to move around ECS using the least memory you can. It's not the best place to use ECS, but it's still a nice way to introduce yourself to it. But yeah, I'll be using it there, and I hope you guys are not confused anymore by this method of doing things. If there's anything else that confuses you, keep letting me know in the comment section down below, or even better, on the Discord. That's a very good story, Carsey. Thank you very much for sharing.